Hi guys, welcome to Learning Electronics Repair. And although it's now officially spring here, it's also Christmas again because I have a package here from PCBWay. So these are some projects that Detlef and myself have been working on. Some of these are effectively completing some previous projects, and we have something else quite interesting as well. So to have a look at these, I think I better find Detlef. Detlef, where are you? Oh, I found him.
What happened?
We've dragged you out of your box for a while, Detlef.
Oh, yeah.
So, welcome again to Detlef.
Hey, guys.
Let's have a look to see what we've been playing with. So, there are three things in here. I'll take them out in order of the, well, what's the most interesting, really, yeah?
All of them.
Okay, so let's have a look at some PCBs. The first of the projects we have in here is effectively, we think, the last iteration of Mr Bleep. So Mr Bleep is working great, but Det decided to make these PCBs. So what was your idea behind these, Det?
Yeah, we were always talking about getting this smaller. And, you know, the original Mr Bleep is a thing that's through holes, so we kept it buildable. But we wanted to do a small one, and this will be our small one from this.
Oh. So this actually takes on a few ideas that people put in the comments, yeah, about these. One of the things that somebody suggested is that we could run these from two CR2032 cells, like CMOS batteries, basically. So that includes that. And the rest of this is exactly the same as the original Mr Bleep,
yeah, we didn't change the schematics here. We simply changed the footprints. Yeah, we went for smaller footprints. These are mostly, I think, 603. Yeah, looks like 603.
Okay, so Detlef said he was going to order some of these, and he also said he was going to be lazy. So, lazy Det. Yeah. For the first time, we actually tried PCBWay's assembly service, and we asked them to assemble some of these as well. So we have a few assembled ones. And this is how they came. You'll notice the CPU is missing the microcontroller. Is this because you need to program them?
Yeah. And we probably need to program them out of circuit before we can put them back in there. I didn't want to switch CPUs, so we could do with 412 maybe. But to keep this in the same state as we had the first Mr Bleep, we keep this solution here. So this means that we will have a prototype with some wires hanging around and a DIP CPU somewhere on a breadboard, and trying this out if everything works. If everything works, well, we're fine and dandy. And we're simply slapping a SMD version of the AT85 there. Okay,
so let's put one of these under the microscope and let's have a close look at the quality of work here.
Please, yeah.
So here we have one of the boards. I know Detlef has ordered pre-built PCBs before from various places. What do you think of these?
Oh, they look great. The thing is always you have to get them the footprint, and they decide what to put on there. But this worked well, and they had a really good communication when they ask, "Oh, is this diode the right way around to send a photo with the anode and the cathode, the power diode up in the top of the
this one up here?
Yeah, this was one of the pictures. And
this one.
Yeah. And they made sure that the diode on the right side and on the right orientation went well.
Yeah, so it's looking good. So, you know, we also have some unpopulated ones of these. And what I thought we might do, actually, on an upcoming video, certainly I'm happy to try this, is to populate one of these by hand to see how it goes. And I also have a hot plate here. I've never actually tried this, guys, so maybe we can do a beginner, i.e. me, in this respect, try to populate one of these boards using solder paste and then a hot plate just to effectively solder all the parts in place at once.
Well,
and yeah,
remember, there's a product coming up where we need to solder them.
There certainly is, actually. So let's practice on this one. Yeah,
that's a good thing.
Yeah, so we'll practice on this one, and maybe you guys be interested if you've never done it before, especially as I've never done it before. Let's see how easy or how difficult it is to use solder paste in that way and populate a board. And I'd be very interested to see how the quality varies between the two hand built.
One thing when it comes to pricing, you maybe think, okay, this must be really expensive when you do the populated things. Remember, you don't have to source them yourself. They simply do this for you. And it's not as expensive as you think, and calculate your time. When you populate the thing, it takes time.
Yeah.
What do you think? How long would it take you to populate it?
Well, we're actually going to find out. So,
20 minutes per board.
No, I think probably longer than that.
Okay, one thing on this board that we're not sure if it will work, just purely by testing, is the buzzer. We ordered this by catalog and thought, okay, this maybe works, and we'll find out.
Yeah, I think I remember the criteria by which we ordered these buzzers is that there was a footprint available on AliExpress. So
yeah, the footprints was a thing, and we wanted to have one and that we can get. These are not easy to get, and you don't want to order 100 pieces from Mauser for this. So
no.
AliExpress is the usual way. But these are pre-assembled too, so
yeah,
we're looking forward to make some noise.
Exactly. So that's that one. You will see this when I try to populate them, and then we will try the buzzer and everything else, so you can see these little Mr Bleeps working. Be interesting to see if Carlos could perhaps make a little case for these 3D printed. Yeah, and that's up and running. So that's that one. And here is another project that we've had ongoing. So these are actually the add-on boards for the Multiload. We made a few videos with Multiload. We eventually got it working. Do you guys remember this thing?
Oh, this is a long time ago.
Yeah, this was a while ago. So this was our upgraded Multiload. It can handle up to 140 watts. It no longer blows transistors up. If you're interested in seeing that, I'll link the old video. So it no longer blows transistors up. And this can either load any sort of conventional power supply, or it can load from USB, and it has a little decoy built on here, so you can even control the USB power supply and set it to whatever voltage you want and load it. So the only thing this doesn't really have compared with like a professional USB analyzer is metering, and that's what these are for. So let's have a look at one of these. This is another one of Detlef's little designs.
Oh, you can read this?
Maybe
switch to the
yeah. Okay.
Oh, look at this.
Now all becomes clear, yeah?
The chip in all its glory,
Yeah. So again, you can see we actually ordered some of these populated, but we have some unpopulated PCBs as well.
Yep. And as you can see here, this is a CPU. We have a CPU on that one, and this was assembled by PCBWay.
Yeah, you can see it there. I mean, this is like a small outline IC, so these are not too difficult to solder by hand, to be quite honest. And what's this? Oh, is this a voltage regulator?
This is a voltage regulator, yeah. You remember the Multiload can do up to, what did we say?
About 30 volts.
30 volts, yeah.
Yeah.
And we needed something to turn on the voltage, because my little CPU won't be happy with 30 volts. So
no.
I put a little voltage regulator on the back side here. This is the AP73 blah something. I can't read this. I can't read the.
Okay.
Yeah, this is probably me doing the silk screen too small.
Do you have a schematic for this one?
I think we have. Yeah, somewhere there should be a schematic.
Let's have a look. Okay, so here we are in schematic land, basically. Although this is the little board view, shall we call it?
Yeah, this is the PCB layout. Yeah, give me. Yeah, this is the right one.
There's the schematic. Again, one of Det's schematics. I'm guessing you guys have got really used to these by now.
I hate it. I hate it because it's all nets.
I know. So I'm getting quite used to this now. So AP7380-33. So this is a 3.3 volt regulator, which could handle, I think it was 35.
Yeah, this
volts.
is why we selected this one. We wanted to have one that has a high input voltage. And I know you could use switch mode. We use so little power in here, we will get away with a linear regulator.
Yeah, it's only driving just the CPU and the display, I guess.
Yeah, and the display will be an OLED thing, so we'll be way below 10 milliamps, I guess. This is all guesswork. We measure this, obviously, can measure this, obviously, when we have the real hardware. And
I think you have one of these assembled, don't you? But I just mentioned, so we actually found this regulator quite, I thought, a bit of an unusual way, but you guys will probably say, if we didn't say, you'd say that's how I would have done it. So we knew what we wanted, but we didn't have a clue of the part number. So we used, I think it was Mouser or Farnell or one of these ones, where you can kind of like put components in, put your parameters like input voltage, output voltage, and we stuck all that lot in there, and it gives us a short list, and this one was there.
This is our normal modus operandi there. If you know what you need, they're so great tools that they're Mouser, DigiKey, my usual go-to part suppliers. If you want to go cheaper, AliExpress works most of the time.
But in fairness, we actually used if it was Mouser or whichever one it was, we used to actually find out the part number of something that would do what we needed, and then we cheapskated and went to AliExpress to buy them.
This is how you do it, guys.
This is the way.
This is the way.
So let's have a quick look at the assembled one of these. So, Det, this is one you assembled.
Well, I sold it for pins, so if this means assembly, I did.
So this is a little, what type of display is this?
OLED. This is an OLED, a 128 by 32 pixels, I think. And it's, you see STL, SDA, so it's an I2C interface there.
So this connects to the actual multi-load unit, you can see here.
There's a display.
Zoom out a little bit. So this actually fits onto here. Like so. If I can just do it. That goes onto there. And then basically here we're picking up VCC, which was the power supply we're loading. Ground and current sensors, a current sense resistor here. And effectively, by measuring the voltage on VCC and measuring the voltage across current sense, we know how many watts has been dissipated here. And we can display incoming voltage, current and watts. So this just needs some software writing. You can probably see it now and understand why we have the voltage regulator on this board, because we don't know what the incoming voltage is going to be.
Exactly.
And as Det says, the microcontroller is 5 volt maximum.
It could run 5 volts. We're running on 3.3 here.
So there you are. I think there was a reason we run it 3.3. Is there something to do with the scale on the current sense?
The reason was that we wanted to have a possibility to display 3.3.
We wanted to be able to load power supplies down to 3.3. I knew there was a good reason why. But I suppose you need a little bit of headroom for the regulator.
Of course. So 5 volts is the usual thing. You normally would use this on some USB devices,
Exactly. So so that's why we use the 3.3. Okay, so that's that one. So to complete this now, Detlef has to go and do a little bit of work programming this unit, and then we can just connect up and we'll try it. And this will do what an expensive USB analyzer would do.
Probably.
And it will also load the power supply as well. And that's the whole point of this. So switchable for USB-C, for PD supply, watts, volts, and current.
On the usual.
The usual. Okay.
The little CPU on here was a choice because I wanted to have an easy way to do this, and I could maybe go slower with that. The AT412 would give me I2C2, but I don't have so much memory in there, so I voted for a 16K CPU. So this should be fine with the OLED display.
Okay, so that's that one, and then we have one more project amongst these PCBs. This is something new for you guys, so let me tell you what we've been working on, and we think this is another first. Yeah, it is. Okay, and here is the third project, and here this is ATXtra 2023. You can see it took a little while for the boards to arrive here.
We were just chatting around and thinking, how did we do that and why did we do that?
Okay.
But it's a revision 0, so this is the first one of these, and fingers crossed as always with the revision 0s.
Okay, so the idea behind ATXtra came from some experiments I did on Learning Electronics Repair, where I was trying to diagnose faults on graphics cards. And I figured out that by measuring the current that the graphics card draws when, for example, you load the drivers, it switches to higher resolution, or when it boots up and detects, you could actually determine effectively if the GPU was running or not, and if it was running correctly or not to a fair extent. So I did some experiments where I actually modified a ATX power supply and added a current meter to it, basically. No, I tell a lie, it was a long time ago. I used my bench power supply to provide the voltage, I had a dual supply, 5 volt and 12 volt, and that's how I did it. But the bench supply could only handle up to 6 amps, I think it was, and I could only test old graphics cards. So this is where ATXtra comes from. So this is effectively a bit like a breakout board that you connect to your ATX power supply that you use for the test work. And you can see we connect the 3.3 volts in and out, ground in and out, and 5 volts in and out. Now, you might wonder straight away why we're doing this and what's happening with the 12 volts. Well, the 12 volts is going directly to the device you're testing, the motherboard, the graphics card. The board then effectively, and this is a populated one, again, thank you PCBWay, you can see they made a nice job of this. Okay, this one effectively, again, monitors the voltage on all the voltage rails from the ATX supply and the current from each supply via shunt resistors. So we have
these things.
Yeah, there's one how they came from AliExpress. We decided we can just bolt these down on here. We can take, for example, all the 3.3 volt wires, cut them from the ATX, we'll use a modular one in here and then out to all the plugs and so on. You would think then that we'd fit one of these on 5, 12 and 3.3 volts and that would all work. And just the last thing, by the way, down here, power supply on. We can start the ATX here with an override. And we can also actually monitor the 5 volt standby current through this resistor. Okay, so this is how we've designed it. And I'll let Det explain exactly why we did it this way, not 3.3, 5 and 12. Okay, so Det just came up with some choice words while I was getting the schematic ready. But Det, this was my idea, but Det implemented. That's the best way. This was very much a joint effort of how we designed this.
Yeah.
So let's have a look at the schematic.
Yeah, when Rich came up with the idea, I'm the guy who only did the designing things. He said, okay, I want to have the current watched of 5 volt, 12 volt, 3.3, and how do we do this the best way? And I said, okay, well, we have these shunt resistors here.
Yeah.
This is the right word?
Shunt resistors.
Yeah. We simply go, okay, we can measure the voltage drop that happens over them. So if I go to the 5 volt thing over here,
yeah,
your mouse still hates me. We have V5 and I5. So I have a different, I can measure simply 2 voltages here.
Okay.
And this gives me the differential between what's dropping on the...
Yeah, what's passing through. So it's effectively the voltage dropped by the resistor, the shunt.
Yep.
We can use that to calculate the current. Yep. And these shunts are 50 milliohms, 0.05 of an ohm each.
Yeah, so we calculated something, there must be 30 amps until we get into something where our ADCs in the little chip will be somehow sweaty.
Yeah.
And 50 amps on this tracks, then you have different problems. And
yeah.
There probably will be fire and explosions around you.
Before the CPU dies.
Yeah. So we think we can get away with that. We find out soon. And when we designed this, we did this all for 5, we did it for 3.3, and then we did a thing here that is a ground return 12 volt indirect. So we measure the current that goes through ground.
Yeah.
So 5 volt, 3.3, 12 volt go out there, and there's something coming back. This must be the same.
The sum of all three.
The sum of all three. And we know the current on the 5 volt, we know the current on the 3.3, we know the current on ground, so we can deduct from there what's the current on 12.
Yeah, we subtract the currents we know 5 and 3, and whatever's left is 12.
Yep.
And the reason we did this is because the ADC converters in the processor can't handle 12 volts. So Detlef initially thought, well, use a voltage divider. But I then said, but if you're measuring the current through a 50 milliohms, the voltage drop is very small, and then you're going to divide that voltage drop by, say, 10 times, so the ADC gets no more than 1.2 volts, and this doesn't work.
No, this doesn't work. We measure actually the... Oh, come on,
move.
We actually measure the voltage over here, but this is just V12.
Yes.
Yeah, this is only for measuring voltage, not for measuring the current.
Yeah, so here you're taking 12 volts, nominally on the power supply, and this divides it down, so we get, I think it works out 1.1 volts or 1.2 volts here.
Yeah, something like that.
For 12, and then we do some mathematics, so we can, on the display with this, for each voltage rail, we will display the voltage, and the current and the wattage.
Indeed. Yeah.
For all three. In fact, for 4, because we're also going to do this for the standby, because this can also be very useful when you're working on motherboards, if you know how much current is drawing from standby.
Absolutely. And down here you see the standby line. So 5 volts standby, so there's a 50 milliamp.
Yeah,
so
50 milliamp.
Milliamps. So we measure this somewhere, I guess.
Yeah.
We probably do.
We do measure it somewhere.
That we do. That we do, yeah.
Yeah. The reason we only use a small resistor for standby is because it can't supply more than about 2 amps anyway.
Yeah.
2 or 3 amps, so we don't need these big shunts that we have on the other rails. So that's how it basically works. I think that's quite an elegant way we've done this.
Yeah, I think so, yeah.
Yeah.
It will be based around an 80 tiny CPU, a 32K unit in this case. 32K because they're available. They don't cost really more, and I have enough space in there to draw the OLED display, but it'll be a bit bigger than the one you saw before. We use a 128 by what's the thing? By 64, I guess.
Yeah.
So because I simply need to display more data here.
And these LEDs, are these just to monitor a quick visual check that the voltage rails are all up?
Absolutely. And you see they're connected to real hardware. There's no CPU between them. So if you connect 5 volts on to ground, the LED will go on.
Yeah. Oh, and this is the power supply on status.
Yep.
So again, you can monitor if the signal's coming back from the motherboard when you press the button.
Indeed.
So really, ATXtra is intended basically as a useful workshop repair tool if you're working on motherboards and graphics cards. Just by connecting this as your known good power supply, straight away it tells you quite a lot before you even get the multimeter out. That was the idea behind it. And I'm interested to know what you guys think.
Let us know in the comments, guys.
Yeah. And also about the design of this. Personally, I think this was a very elegant way of doing it by using the difference to calculate the 12 volts. But comments below, guys. We did realise, by the way, when we were working on this, that effectively you've got 2 shunts on each power rail, because whatever power is going through the 3.3 or the 5 comes back via this one. But the 12 volts, which is where most of the power is being drawn from on a PC, only goes through 1 shunt. Yeah. So by having 2 shunts on these 2, you will effectively drop the voltage a very small amount. But because these are only 50 milliohms, the 3.3 and 5, which are passing through 2, is going through 100 milliohms. So it really doesn't, I don't believe it'll have any effect on that. So yeah, that's ATXtra. ATXtra. I hope you like the logo. This is Detlef's work. So Jet, any final words on this one?
Oh, I'm really curious how this turns out. Yep, this is a thing I haven't thought before, and when Rich came up with the idea, I thought, yeah, could work. Let's see what happens. Yeah.
These PCBs are very heavy, by the way, because there's heavy ground planes and power planes in here. You guys won't see, but when I'm picking this up, it almost feels like, and you have it, feels like an aluminium PCB.
Oh yeah.
It's so, yeah.
Nice sound.
It does a nice sound. Yeah, it even feels like an aluminium PCB, like the type of thing you find on LED floodlights and that sort of stuff.
Yeah.
Okay, so thanks once again to Detlef for his input with this. I certainly wouldn't be working on these projects without Det. That's for sure. Nice. Thanks PCBWay, of course. PCBWay again. Thank you very much for the effort you put into building these things for us.
These guys are great partners. Yeah.
Absolutely, and you guys for watching. Thanks. Okay, see you all soon.
Bye for now.
Bye, nerds.